Hello, everyone. Thank you for so much for joining my session today. Let me ask you a quick question. Can you pod survive a restart? Pod restarts might sound basic, but handling them correctly is a bit challenging. Kubernetes restarts pod in many situations, and if your pod isn't ready for prepare for that, you could run into unexpected issues. Before we dive in, let me briefly introduce myself. My name is Ozawa. I'm a member of technical staff at CloudNatix. I'm currently developing LM Marina. It's an open source AI platform for Kubernetes. So today, I'm going to show you some insights I learned over the years. Here is today's agenda. I'm going to show you how to reduce the impact of restart using 3 different types of applications as an example. Let's move on. So, why does restartability matter? It comes down how Kubernetes treats your app. You might have heard the famous analogy, Kubernetes treats your app more like cattle rather than pet. But what does it mean? If your application is a pet, it requires special care, manual intervention every time it goes wrong. But Kubernetes is optimized for cattle. In fact, many powerful features such as self-healing, rolling upgrade, and autoscaling fundamentally rely on restarts. So take advantage of those powerful features. Pod restartability is important. A restart isn't just a single scenario. We'll dive into the detail later, but for now, let's get a high-level overview. At the container level, if your container exit or liveness prove failure, the Kubernetes restart it. And second, at the replica set level, even if your pod gets deleted, it automatically recreated by the controller to keep the desired replica count. At the deployment level, during a rolling upgrade, unlike the previous 2 scenarios, deployment creates a new pod first before deleting the old one. So, how can we ensure our workloads survive in these scenarios? Let's examine the simplest scenario, a basic pod deletion and recreation flow. We have a simple deployment. This defines only image and arguments, but doesn't handle any signals. Let's say we delete its pod using kubectl delete pod. Firstly, this pod receives a stop signal, usually sigtime. However, if the application doesn't handle the signal, it continues running during the default 30 grace period. Once that time is up, the pod is forcibly stopped with sigkill. Meanwhile, the number of running pod drops below the desired number, so the pod is recreated. Then scheduling, image pulling, and container startup all happens as usual. Now, you might wonder why the pod keeps running even after it receives sigtime. If you run some program on your laptop and send it sigtime, it's typically terminated. However, in the container world, application typically runs as PID1. So the Linux kernel treats it specially. If your application doesn't handle sigtime, it's just ignored. That's why the process keeps running until sigkill. And here's a problem. If your application just waits the entire grace period, that can waste resource. Also, your application has shutdown tasks like closing connections or writing back data. Sudden shutdown can lead to request loss and inconsistencies. To avoid this, it's important to handle the stop signal and shut down app before the graceful period ends. However, some application needs a different signal for graceful shutdown. For example, Nginx expects SigQuit, But what if you can't modify the application code directory, like those third-party applications? In such cases, there are two solutions, Dockerfile stop signal and Kubernetes pre-stop. In the Docker file, you can set stop signal to tell which signal your application expects. In this example, we set secret, so container gets secret instead of sigtom. The second method is pre-stop actions, which runs just before the container shutdown begins. There are several options. First, with an exec hook, you can send the desired signal directory, like using kill secret. But it's required kill binaries in your application container. Second, HTTP hook is another option. It calls a shutdown endpoint on your app, which is useful if your application provides the HTTP-based Graceful shutdown. The last thing is the lifecycle stop signal. This feature isn't available yet, but you will be able to specify custom stop signal directory in the pod manifest soon. This is useful because it works like Dockerfile stop signal, but you don't need to rebuild your image. So now we understand how termination works for a single container pod. But what happens when your pod has multiple containers? For primary containers, the termination process all happens at the same time. But what about sidecars? The sidecar design pattern, which is extend the functionality of the primary container, like logging agents, like that, has been known for many years. But sidecar support as a native Kubernetes feature is relatively new. It becomes a default starting in 1.29. This feature builds on the init container, and it's only applied when the pod restart policy is set to always. So here, how the shutdown works. Unlike primary container, sidecars shut down sequentially. Once all the primary containers have exited, the sidecar gets stop signal one by one in the reverse order of how they started. In this example, sidecar stop in the order 3, 2, 1. One thing to keep in mind, the pod termination grace period is shared by all containers, so make sure everything can finish in this period. So far, we've learned a graceful shutdown. However, pod termination grace periods are not always guaranteed. Of course, if your app crashes due to bugs or get killed by killer, there's no grace period. And even when Kubernetes does trigger termination, it can sometimes be overridden or ignored. For example, duration and eviction API can override this period. For example, if you run kubectl delete pod with a 1 second grace period option, the pod will be immediately terminated regardless of its pod grace period settings. Also, when a node is under severe resource pressure, the kubelet evicts pod to reduce node usage. In a soft eviction, this is disabled by default, but kubelet overrides it by its configuration value. And harder eviction is more aggressive. Pods are immediately evicted with any grace period. So we've explored the standalone applications restart, but how about applications that handle network traffic, like HTTP servers? Let's consider deployment with a service. When you delete a pod, Kubernetes sends a stop signal, as we learned before, then eventually removes the pod from the routing table. A new pod starts up, and once it's marked as ready, traffic is directed there. However, even if we've implemented a graceful shutdown, it's not enough to guarantee zero downtime. We still face two challenges. Let's look at the first issue. On the right, this Go code shows a typical HTTP server. After receiving shutdown, the shutdown function is called for Graceful shutdown. And this function keeps handling in-flight requests, but stops listening immediately. Here's a catch. The server stops listening to new requests, but new incoming requests will still be routed to your pod. It's causing a request drop. To avoid this problem, shutdown should be delayed until Kubernetes stops routing traffic to the pod. There are some ways to introduce this delay. One is just modify your application code and adding sleep before the shutdown logic. Another way is pre-stop sleep. From 1.30, this feature is available by default. So you can set sleep seconds in the pod manifest directory. Let's move on to the next challenge. If your app isn't prepared right after its startup, but Kubernetes immediately starts sending requests, these requests can get dropped. Readiness probe can solve this problem. This probe checks whether the application is actually ready to handle the request. Kubernetes will start routing requests only after this probe passes. However, using only a readiness probe has limitations because this probe checks the status throughout the entire container lifecycle, not just during startup. Generally, you need different thresholds or intervals for startup and post-startup probes. If you rely on a readiness probe for each phases, it could lead to slower startup or too strict health checks. That's where startup probe comes in. This probe runs only during the initialization phase. Once the startup probe succeeded, readiness and liveness probe take over. This separation lets you configure startup probes without affecting the post-startup probes. Next, let's see the actual behavior the restart. On the left, we have deployment and service manifest. It doesn't have special settings. On the right, this is a corrected version deployment. It's added pre-stop sleep and proofs, which ensure smooth traffic transition with zero time. Let's see the failure case first. On the screen, each panel shows the failure case, deployment spot, and the service endpoint. And now, I'm going to delete the pod. Look at the log. Our server received a shutdown and start the shutdown. However, IP table haven't been updated yet, and traffic is still being directed to the pod. As a result, these requests dropped. Now, Kubernetes has created a new pod, and the routing has switched, but we still see failures. This is because the new server isn't ready to handle requests. So next, let's see how we can avoid these issues. Here the corrected version of deployment, which has pre-stop sleep and proofs. Now, I'm going to delete the pod again. This time, thanks to pre-stop sleep, Kubernetes waits 4 seconds before sending the shutdown signal. While an old pod is sleeping, a new pod is created. The readiness probe returns success. Once pod and endpoint are ready, the IP table will also be updated. As you can see, traffic smoothly transitions without any drops. Finally, the old pod receives shutdown and exited. This way, by applying pre-stop sleep and proofs, we can minimize downtime during the pod restart. We've covered traffic handling during restarts, but we haven't touched when the traffic shift happened exactly. Normally, kube proxy do not send the traffic to terminating pods, but if no other endpoints are ready, traffic still goes to the shutting down pods. This will change the restart behavior depending on replica counts and restart types. In multi-replica scenarios, Kubernetes removes the endpoint almost after the pod is deleted. Then it adds the new pod endpoint once it becomes ready. Of course, there are gap between the old pod stopping the new and the new one being ready, but it doesn't matter because other replica can still handle this request. Next, in the routing upgrade, new pods are created first, so regardless of replica count, traffic will be switched when the new pods are marked as ready. But one point, note that traffic doesn't stop at the same time of duration. Components like kubelet, endpoint slice controller, and kube proxy, all components fetch resource status from API server and process them asynchronously, so there could be a slight delay. Then, how about a single replica workload? As I mentioned, if there is no other ready endpoint, traffic keeps going to the terminating pod. As you can see on the left, the old pod keeps receiving traffic after it started shutting down. Once the new pod is ready, the traffic is switched. With this seamless traffic shift, even if it's a single replica workload, we can avoid request drop during restarts. However, as we learned in the previous demo, if the old pod ends too quickly, the new pod can take over this request. There is a risk of request drops. Therefore, giving enough pre-stop strip and setting probe is important. Next, let's look at what happens when a liveness probe fails in a single replica. In the container level restart, all events happen sequentially, so there's a short gap before it comes back. Unlike the routing upgrade case, no one can take over this traffic, so during this gap, the request is dropped. That's why in some cases, we cannot avoid downtime in a single replica, so multiple replicas is recommended for important applications. Now, we learned about simple app and HTTP servers, but what about controllers? We can apply the same approach to controller, but with one extra factor, which is a leader election. Typically, the controllers implements leader election to prevent conflicting upgrades. So let's focus on that. Here, we will take the controller runtime as an example. This is a commonly used library to implement a controller. In this library, once the controller gets signed down and the context is canceled, the grace shutdown begins. It goes through several termination procedures and finally stops renewing leadership. Then new reader gets a leadership. So how can we reduce disruption during re-election? Before talking about the optimization technique, let's see the Kubernetes leader election behaviors. Kubernetes provides a list resource for leader election. Each candidate continuously tries to update this shared resource. And the first pod that successfully updated becomes a leader. Here are two key parameters that affect reader transitions. First, list duration sets the maximum leader duration without renewal. The default period is 15 seconds. Second, retry period specify how frequently candidate attempt to acquire leadership. The default interval is 2 seconds. With these default values, in the worst case, a leadership takeover could take 17 seconds. You might think we could just shorten leader duration to reduce takeover time, but setting a too short period increases split brain risk, like multiple pods believe they are a leader. So how can we safely reduce this time? The controller runtime provides an option called leader election release on cancel. When enabled this, the leader proactively ends the leadership, not just waiting for expiration. Internally, the manager updates least duration seconds to 1 second only at the end. With this configuration, the leadership transition time can speed up to 3 seconds while keeping the default duration except on termination ends. In summary, although careful attention is required, temporary least duration updates allow you to safe and rapid leadership transition. So far, we've discussed how application can gracefully handle restarts. But what if cluster maintenance trigger multiple restarts and affect the entire workload? How can we minimize these disruptions? Pod disruption budget called PDB can limit these voluntary disruptions. On the right, we have two manifests, a deployment with 2 replicas, and is secured by a PDB. This PDB allows only 1 pod to be unavailable. In the scenario on the left, the eviction request succeeded because it respects the budget we've set. But in the scenario on the right, the eviction request is rejected. This is because another pod is still pending and the eviction would exceed the budget. In this way, when you set up a PDB resource, it will reject requests that would violate the disruption budget. So you can reduce disruption. We found the PDB is beneficial to reduce those disruptions, but there are some limitations. First, unlike rolling upgrade, pod eviction doesn't create a replacement pod ahead of time. So if you want to keep at least 1 pod during eviction, you need at least 2 running pods to begin with. Second, if you set PDB too strictly, it could permanently block eviction requests. This would happen in several cases, such as when workload has only a single replica, max unavailable is set to 0, or the application is never in a running state due to bugs or something like that. This can complicate node maintenance like kube drain, and it requires a lot of manual intervention. I mentioned that application bug can also block this eviction, but Kubernetes provides this solution. Starting from version 1.27, Kubernetes supports unhealthy pod eviction policy as a default. When you set always a load to this policy, unhealthy pod do not block the eviction request. Lastly, remember that PDB only applies to the eviction API and that's of preemption. Of course, if you delete pod, PDB constraint won't be worked. Also, when the scheduler tries to preempt lower priority pod to make a node space, it normally will follow the disruption budget, but it finds no place match those constraint budgets, in which case preemption may ignore the PDB. So finally, let's move on to the key takeaways for today's sessions. First, make sure your application can handle sig time and start Graceful shutdown. If another signal is needed, use stop signal or pre-stop actions. Also, sidecars are terminated sequentially in reverse order of their startup time. And remember, the pod termination grace period is not always guaranteed. Next, Pre-stop sleep and readiness curve help minimize traffic downtime. Both features support smooth traffic shifting during restart. Third, if your controller uses leader eviction, you can speed up the takeover time by setting in short period as a least duration only at the manager stops. But be careful for split brain. Lastly, PDB can mitigate the impact of voluntary disruption without losing all workload replicas. These practices will help make your pod more restart-friendly and take advantage of Kubernetes automation features. And last, here's some resources. This slide has been uploaded to the event site, and all examples are available on my repository. That's wrap up our deep dive pod restart session. Thank you.